Hello again, my little cherubs. So this is the last session for this week, and as it says there, it's on motion in gases and density. So we're going to start off by looking at this little diagram here. This is something that you should know. It is a typical particle model for a gas, where you've got the particles showing no bonds between them, showing that they are moving randomly. They've got lots of space. They're moving quite quickly, which is indicated by those little lines. And you should know what that means. Now then, when you put gases into a container, you start talking about gas pressure. And the reason that we get gas pressure on the inside of containers is because, as we've just talked about, the particles move randomly. And as they move around, they collide not only with each other, but with the insides of the container. All right, now this is called gas pressure as they are moving around and as they are hitting the inside of the container. Now then, in an exam situation, you might get two different types of containers. You might get balloons, you might get tyres, anything really that can be inflated with air or inflated with a gas. All you've got to remember is this, and is that as gases, as the particles move around, they will be hitting the inside of the container and they will be exerting a pressure, so on and so forth. Okay, and we'll get on to more detail about that in a second. All right, so keep that particle model and the motions of gas particles in your head as we continue. Now then, sometimes you might be asked why gas pressure increases. So you can increase gas pressure in two ways, either by reducing the volume of the area that your gas is in, or by increasing its temperature. And we'll talk about temperature in a second, but we're going to talk about decreasing the area, the volume first. If you squash a gas, you also increase the pressure that gas is under, or the pressure that those gas particles exert. And that's because you've got the same number of gas particles as you had previously. Okay. You got 8 there and you've got 8 over here. But what happens is in here is that because you've decreased the space, you have increased the collisions between the gas particles and each other, and the gas particles and the side of the container. And what that does is increases the pressure, because all pressure is, if we look over here, gas pressure is the total force exerted by all the particles on a unit area of the container wall, or of anything really, of any container or anything where you've got pressure being exerted. Now, pressure can be in newtons per meter squared, pounds per square inch. You probably heard pounds per square inch if you're talking about bite pressures and things like that, you know, crocodile bite pressures and shark bite pressures and stuff like that. All right, but it's within a sealed container, sometimes referred to as an enclosed system usually, which is what we talk about. So which is why we don't talk about pounds per square inch, but I just want you to just kind of like think about where you might have heard pressure per unit squared before. All right, so if you want to increase the gas pressure, you need to increase the total force exerted by all the particles within a container. Okay, so you can do that by increasing the pressure by decreasing the volume, or by increasing the temperature. So here's a question for you. What effect would increasing the temperature have on pressure? Okay, now this is probably quite a common question that you get in exams, and here is what you would say. Okay, so what you've got here is you've got more thermal energy. Okay, because what happens is as you increase the temperature, you increase the thermal energy. That gets transferred to the kinetic store of particles. Now, because the particles now have more kinetic energy, more temperature essentially means more movement. And if you've got more movement, more kinetic energy of the particles, you're going to have more collisions. If you're going to have more collisions, you're going to have more collisions with the inside wall of the container, therefore an increased pressure. Now, this is conversely happens if you decrease the temperature. So example, if a bike is kept out during winter and you go to ride it, you might find that the tyres look a bit flat, but there is no obvious puncture. What's happened here is that the thermal energy store has been depleted, or it's been decreased because there's less thermal energy available, which means that the kinetic store of energy in the particles has decreased. What this means is that if you've got less temperature, you've got less movement, less collisions, and less collisions, you have a decreased pressure. So what happens there is that the tyre deflates. Same as if you put a balloon in a fridge or a freezer. They do these strange examples in exams. Don't feel thrown by them and thinking, why on earth would anybody ever do that? They only do these strange things in exam situations, but it is an example of what is going on here with this kinetic store of particles. Okay? Hope that makes sense to you. Right, now then, the next thing and the last thing we're going to talk about today is density. So density is calculated by the mass divided by volume. So the density is essentially how compact a substance is. So basically how many particles there are within a substance. And you can work that out because it relates the mass and the volume of a particular substance together. So you can work out the density by dividing mass by its volume. And it's either in kilograms per meters cubed, or it's in grams per centimetre cubed. And so there you are, there are your units. Okay, now then whenever you're doing calculations, remember that you always have to round to two significant figures, please, ladies and gentlemen. If you do not do that, you are throwing away you are throwing away marks in an exam. Okay, so it's absolutely essential that you always round to two significant figures, unless told otherwise. Right, moving on. Here is an example. So an example here is a gold bar has a mass of 12 kilograms and a volume of 6.3 times 10 to the minus 4 meters cubed. What is the density of the gold bar? Okay, pause it here. Work it out. I want to see worked examples, please, ladies and gentlemen. Okay, and our answer is here. So it's density equals mass divided by volume. So it's 12 divided by 6.3 times 10 to the minus 4 equals 19.047.6, blah, blah, blah. Remember, we're rounding it to two significant figures, so it's 19,000 kilos per meters cubed. Okay? Good, right. So that's how you work out density. Now, last thing we need to look at is how you would work out density in a practical way. Okay, so if you look up here, our density practical, there's two ways to measure density. You've got a regular and a regular shaped object, which are solids and liquids. Okay, so we'll look at liquids first. All right, so liquids, what you would do is you'd set up a practical like this. So this is your electronic balance, and you've got your measuring cylinder, and you've got a liquid that you want to work out the density of. So what you do is you zero your balance. So you have your 0 on your balance. All right, pressing the little tare button. All right, then you would add 10 mils of the liquid. All right, and you would record the mass. All right, simple as that. Then you repeat that again, okay, adding another 10 mils, all right, so now you've got 20 mils in there, all right, and you then divide that by the mass. Start again. So you add 10 mils of liquid and record the mass, and you add another 10 mils of liquid and record the mass, and another 10 mils, and keep going until the measuring cylinder is full, or it's at the top of the recording. You then calculate the density, remembering that 1 mil, okay, is 1 centimetre cubed, and you do that for each of the 10 mil volumes that you've added. So you do it for the 10 mil and the 20 mil and the 30 mil and the 40 mil, blah, blah, blah. And then finally, you take an average of your calculated results, and this will give you the value of the density of the liquid. Nice and easy there. All right. Now then, regular shaped objects. This is the easy peas method. All you've got, so basically, if you were given a block of whatever it was and you weren't quite sure what it was, you would measure the length, the height, and the width. At this point in your scholastic careers and in your maths, I'm praying that you know what... Let me just quickly draw a 3D object. I'm praying that you know what the length, width, and height is. Okay, so this is the length going that way. This is your width. And this is your height. And I'm praying that you know that, okay? Because if you don't, I'm going to be having words with your maths teacher. All right, so measure the length, the height, and the width, okay? And then to get the volume, you just times your length, your width, and your height together. Nice and easy. The mass, you find it the same as you do over here by sticking it on a balance and weighing it. So your density is your mass divided by your volume. Boom. Easy peas. Now then, if it's an irregular shaped object, you need to look at something called displacement. Now I've put Archimedes at the bottom here because this can is called a Eureka can. And Archimedes, and hopefully you know that little Greek legend of Archimedes running naked through the streets of Athens screaming Eureka because he'd figured out how to work out the volume of an irregular shaped object. And this is how we do it. You get the mass of your object by sticking it on a balance. That's nice and easy. It always starts the same way. Okay, now then, A Eureka can is usually a silver can, okay? And what you do is you fill it up to water just below this spout on the side of it. And underneath that spout, you place a measuring cylinder. You then pop the object into the measuring cylinder, and what happens is that the volume of the object will be displaced, okay? So the water, because you might think about it, every time you get into a bath, okay, the water rises in the bath, and that's because your mass has displaced the particles of water. Okay, you've added yourself to it. So what's happened is that if you add the volume of this object to here, it's going to overflow. And what you're going to get is you're going to get a volume into your measuring cylinder. And that is the volume of water that's been displaced. Now, remember what we said over here, 1 mil equals 1 centimetre cubed. So if you displaced 10 mil, that the object of that volume is 10 centimetres cubed. So to work out to work out density, it's just mass divided by volume. So it's this here divided by this there. Nice and easy, okay? I've just put Archimedes on there because that's it. Archimedes' principle, it's called. Okay, that a solid object will displace the liquid. All right, and that is all you need to know on density of materials. And that's pretty much this entire topic done. So we've done the particle model, we've done the changes of state, we've done the density of materials, we've done specific latent heat, and we have also done the motion of particles in a gas. Okay, so pretty good work, everybody. Right, so I'll leave it there for today. I'm going to put the work that is associated with all this on to Google Drive for you to complete, and I will speak to you all very soon. Stay safe. Bye.